Today's presentation looks at electron configuration and the use of the periodic table to determine the electron configuration of a given element based on its location on the periodic table. When we look at the periodic table, we can see certain regions that show themselves in the table, and those regions include this section of the table, this section of the table, this is helium. I did not include helium. And then we also have this region. And then our fourth region would be this area down here. If we count the width of the sections of the periodic table, you'll see that here we have essentially 2 elements wide. In this section we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 wide. In this section, except for helium, we have 6 wide, and in this section down below we have 14. What these numbers represent, obviously, is the number of electrons that it takes to fill an individual sublevel. It takes 2 electrons to fill the S sublevel, 10 electrons to fill a D sublevel, 6 to fill a P sublevel, and 14 to fill an F sublevel. Because of that, we call this the S block, the D block, the P block, and the F block of the periodic table. Besides blocks, it's also important to recognize that we have horizontal rows on the periodic table. Well, that's not very horizontal. Horizontal rows on the table. These are called periods. There are 7 periods, as you can see here. And we also have these 2 down here that actually fit right into this zone between here. So between 57 and 72 we get 58 through 71. We also have, besides periods, we have columns. And those columns are known as families or groups. And we have a couple of different ways of naming those, naming the groups. They include the 1 through 18 system, which is now the most common, so just standard numbers, 1 through 18. But we also have some systems that involve Roman numerals and letters. You may need the Roman numerals and letters at certain times solving certain problems, but primarily we're going to do the 1 through 18 system. So there are 7 periods, 18 families or groups. The F block down here does not have family numbers. They fit into this area and they actually slide all of the families over. So these are not assigned families. So in reading the periodic table, as we look at the blocks, this is the S block. All elements in this particular family are going to end, or these 2 families are going to end with NS1 or NS2, where N is the energy level number, but N is also the period number. So the very last thing that you would write down in an electron configuration for these elements, this one is in N is 1, first period, S1. So this is 1S1. This one ends in 2S1, 3S1, 4S1, 5S1, 6S1, and 7S1. Members of this family begin 2ns2, 3s2, 4s2, 5s2, 6s2, 7s2. We actually have over here helium, which is going to have an electron configuration of 1s2. It actually fits by its ending electron configuration in this location. However, because it behaves like the other members of this family, which are the noble gases, it's placed over here by chemical behavior, but its electron configuration fits here. If we come over to this side, with the exception of helium, this is the p block. These elements are going to end on the left with NP1 over to NP6, with the exception of helium. So this one will end NP6. So if we're looking at family 2, which is the first, period 2, the first period to actually have a p sublevel, this is going to be 2p1, 2p2, 2p3, 2p4, 2p5, 2p6. And of course we're going to increase as we go down. This is 2p1, 3p1, 4p1, and so forth. Over here we would have 3p6, 4p6, and so forth the rest of the way down. And all those in between would fit into their particular categories. So if we have the D block, that's what we would have here. This side ends in n-1 D1 to n-1 D10. Okay, so this is going to end in n-1, which is 4 minus 1 is 3d1, 3d2, all the way over to 3d10. If we were down here, this would be 5d1, 4d1, 4d2, 4d3, and so forth all the way over to d10. In the F block, this is going to end with n-2 D1 through 14. So this would be 6 minus 2 is 4F1. This would be 7 minus 2 would be 5F1, all the way over to 4F14 to 5F1. So let's look at how this could be used to actually determine an electron configuration. Let's start out with element number 8, which is right here. This is the element that we're looking at. When we read the periodic table to get an electron configuration, we actually begin at the beginning. So we begin with the first energy level, then we go to the second energy level, and third. So we begin at energy level 1, and we go to higher values. We also read left to right. Another important thing is knowing where boundaries are between blocks. So just as an example, we have a boundary right here between family 2 and family 3. That separates the S block from the D block. We have a boundary here that separates the D block from the P block. And it also, as you can see, if we're on period 2, we're going to go straight from the S block to the P block as we move left to right across the table. And then right here, we have a boundary that goes in between the beginning of the D block and the F block, and then a boundary here that represents the end of the F block before we go back to the D block again. 71 leads to element number 72. So if we're going to do family number 8, we're always going to start on period number 1, and we're going to go to the most full element on the family in the section, which is going to be the farthest to the right of that section. So as I read, I'm going to point out in red the locations that I'm looking at. So on the first family, the only time I would stop at 1s1 would be with hydrogen. I'm always going to go 1s2. Okay, so I would write element number 8, 1s2. I go down to I'm at the end of this period, so I go to the next period, period number 2, and I go to the next boundary line here, which is energy level 2, S2. And I move myself across to the right until I hit another boundary line, which is actually here. I didn't put that one in. This boundary line is the end of the P block. So I go all the way over. If I go all the way to here, I would end in P6. But that's not where I actually need to end up. I need to end up here. So I'm going to end somewhere between P1 and P6. I'm on the second period in the P block, and I'm the 4th element over P4. So the electron configuration for this element is going to be 1s2, 2s2, 2p4. So again, I'm reading across, starting with my first element here. I read myself across until I get to the boundary line between blocks. That will be here. Then I drop down to the next line, read across until I get to here. And then I read across until I get to here, to the location of the element that I'm interested in. Okay, let's try another element, number 21. Okay, so this is the one I'm interested in. Using my boundaries, I'm going to go to this element. That's going to be 1s2. I go to my next element, 2s2. To my next, 2p6. To my next, third period S block, second element. To my next, third period P block, sixth element. To my next, fourth element, S block, second element. And then I arrive at this one, so I'm now in the, remember this section is n minus 1d, 1 through 10. So I'm n minus 1. I'm on period 4, so I'm going to go back to energy level 3, D block, first element. And that would be the final configuration. So again, I'm bouncing to the edges of the sections. This one always 1s2, then 2s2, 2p6, 3s2, 3p6, 4s2, then n minus 1, 4 minus 1 is 3, D, first element. All right, element 32. So I'm going to scope out my elements first. I'm going to start with this location, drop down to the next line, go to this location, then across to this location, then down the next line to this location, then to this, then to this, then I've got a D boundary here, and then 1, 2 over. Okay, so 1s2, first period S block, first element, although remember helium is unique. Second period S block, second element. Second period P block, sixth element. Third period P block, second element. That's an S. S block, my mistake. Third period P block, sixth element. fourth period, S block, second element. Remember, in the D section, it's n minus 1d, 1 through 10. So I'm on the fourth period, so 4 minus 1 is 3, D, 10th element, and then I'm back to the P block, which is going to be 4, wrong period, fourth period, P block, and I'm in 2 elements over. Notice that we are not really looking at how many electrons they have. The atomic number is there, but we're not adding it up to see if it actually comes up to the proper atomic number, although it does. And we're also not considering what the identity of the element is. We don't really care here. We can get its electron configuration just by the location on the periodic table. We're also, in doing this, we should be recognizing that the periodic table structure is the Aufbau principle. It's put together that way. Okay, let's try another. Element 17. So we've got 1s. We're going to go from 1s2, 2s2, 2p, sixth element, third energy level, S block, second element, and then we're 1, 2, 3, 4, 5 over, so we're going to end up with 3p5. So rewriting 1s2, 2s2, 2p6, 3s2, 3p5. And let's do one more. Element number 51. Okay, we're reading across. Remember, always begin with 1s2 unless hydrogen is your element. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, and now we're in 5p, 1, 2, 3 elements over. So we've got 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p3. Final configuration. Now you will notice that we have, as we go through this, we repeat things. For instance, we always have 1s2 is going to be the starting point unless hydrogen is our element. We go through the entire second energy level, then the 3s2, 3p6, 4s2, 3d10. We have some things that we repeat. Redundancy just means repeated. So usually in English, redundancy is considered a bad thing, so to be repeated is something that we can cut out. We might have an ability to do that. So to abbreviate, to cut out that redundancy, what we have to know is on an electron configuration, we have to have a place where we decide we're going to use as a reference frame for our periodic table. That would be the noble gases. When we look at the noble gases, and I've got them listed on this blank table, from element number 2 down to 118. And what we would have here is we can use this as our reference frame. Remember that this is actually a very important group, which is the reason for using it as the reference frame. We could really use any family on the table, but this is a particularly important one because it's sort of a target for what we want to do when we talk about chemical bonding upcoming. So if we're going to abbreviate, let's do the unabbreviated electron configuration for element number 14. We would have 1s2, 2s2, 2p6, 3s2, 3p2. So 1s2, 2s2, 2p6, 3s2, 3p2. So when we look at this, if we look at just 1s2, that represents helium. When we go all the way out to 2p6, all of this represents, from here to here, represents neon. And then our next noble gas we don't reach. So what we can say is that instead of saying 1s2, 2s2, 2p6, we can rewrite that as the element whose symbol represents that configuration. So we can rewrite this as neon. That takes care of the first 10 electrons, 3s2, 3p2. This would be the abbreviated configuration. So if we were going to do this from scratch, what we would do, erase here, what we would end up doing is going to find the element that we're interested in, which is element number 14. We go to the last noble gas before we get to that element, which is here, and we start out with that configuration. So we say neon in brackets. Then after neon, we go to this location, then to our element. 3s2 is this element, 3s2. Then we're in the third period, P block, second element. Okay, so let's try element number 53. Okay, we go to the next period up, find our noble gas, which will be right here. So we start out with krypton. That takes care of 36 electrons. We then go from there down to our next boundary, 5s2. Straight across to the next boundary. 5 minus 1 is 4d10. Then we're in the fifth period, P block, 1, 2, 3, 4, 5. 5 elements. Krypton, 5s2, 4d10, 5p5. Element number 57, we can take care of the first set of electrons by going up one period and over to our noble gas. That would be xenon. So we start out with xenon. Then 6s2, 6 minus 1, 5d1. And that's the final configuration. You're cutting off all that redundancy at the beginning of writing the same things over and over and over again. All right, next element is element number 62. So 62 is down here. I have to be careful with this one when we end up in the F block. You'll see why as we go through it. But first of all, 62 is on period 6. So this is our period that we're working on. So we go to the next period up, over to the right, and we find xenon. So our periodic, our noble gas is going to be Xe. We place Xe, place it in brackets. The brackets are part of the notation. After xenon, we go to this location, which is 6s2. From there, we go to this location, because we've got to get that one element in. That would be 5, 6 minus 1, 5d1. And then we have, remember this is n minus 2, so from there we're going to come down to our element. So we're n minus 2, 6 period minus 2 is 4, f, 1, 2, 3, 4, 5. So the tricky thing here is that we had to remember to include this electron, this element, because 57 here comes before 58 here. Okay, so final configuration, at least our predicted configuration. Okay, element number 28, looks like we're moving back up the table to right here. So we're in the 4th period. That means we're going to come up 1 to argon. So argon begins it. That takes care of the first 18 electrons. Then 4s2. And n minus 1 would be 3d. 1, 2, 3, 4, 5, 6, 7, 8. We do that again. 1, 2, 3, 4, 6, 7, 8 is correct. Now, I would like for you to try completing the abbreviated electron configurations for elements 37, 58, 33, and 52. Have these in your notes when you submit them, and be prepared to answer questions about them when you come to class. Our last stage in this is determining electron dot diagrams. Electron dot diagrams show valence electrons as dots around an atomic symbol. First of all, a valence electron. These are electrons that are in the highest occupied energy level. The HOEL. Okay. The atomic symbol represents the atomic nucleus and the core electrons, whereas dots represent the valence electrons. So in drawing these, the first step would be to write the regular electron configuration. You can do this abbreviated. Then identify in the abbreviated configuration the valence electrons, or the hole. Then use the Aufbau principle and Hund's rule to position valence electrons around the symbol. All those steps have to be followed. So we'll start with a simple one, hydrogen. And use a periodic table to assist you with this. This has an atomic number equal to 1, so we would have the electron configuration of 1 for hydrogen as 1s1. There is no abbreviation for hydrogen, just because there's no noble gas that comes before it. We then take the symbol for hydrogen, that represents the nucleus of hydrogen, and we have 1 dot. I'm going to place the 1 dot above the symbol for hydrogen. In general, if we have a symbol, we're going to put s electrons on the top, p electrons around the sides. So we only have 1 s electron, 1 dot on top. Carbon comes next. Carbon has 6 electrons. This is going to be abbreviated if you look at your periodic table. Helium, 2s2, 2p2. So this is 2 electrons plus 2 is 4, plus 2 more is 6 electrons. Place our symbol, C. That takes care of these electrons and the nucleus. And then our highest occupied energy level is energy level 2. We have 1 pair of electrons located here, and we have 2 electrons located. In fact, if you think about this from the standpoint of orbital diagrams, we've got an up arrow and a down arrow. So a pair of electrons, that's 2 dots. And then in P, we've got them separated into 3 orbitals, and we're going to have 2 that are spinning parallel in separate orbitals. So we separate those to show that they're separate individual electrons rather than pairs of electrons. Sulfur would be our next. Sulfur has an atomic number of 16. So we would have, as a noble gas, we would take care of the first 10 with neon. Then 3s2, 3p4 would be the electron configuration. So sulfur, with the symbol S, we have, looking at the orbital notation is, I think, helpful. This would be the orbital notation, so we've got a pair of s electrons, and then we've got a pair of p electrons and 2 single p electrons. All right, zinc. Zinc is on the 4th period, which means we're going to use a noble gas of Ar, 4s2, 3d10. This is a little bit tricky because we have to choose the highest occupied energy level. That highest occupied energy level is energy level 4. So if we do this, the only electrons that we're going to represent would be the 4s, so we would have Zn and a pair of s electrons. These electrons are in energy level 3. 3 is less than 4, so they are core electrons, not valence electrons. Lead would be atomic number 82. It's on the 6th period, so we begin with xenon. And we're going to go xenon 6s2. Then we'll do 4f14, 5d10, and then 6p2. So our valence electrons would be energy level 6. S2, P2. So lead, Pb, 2 dots, 2 singles. I'd like for you to give this a try with magnesium, chlorine, krypton, zirconium, and francium, and give the electron diagram for each of those. Again, have those in your notes when you come to class. That's the end of the presentation.